Hi everybody, my name's Lexi, and I'm diving into the science behind scuba and how you can experience outer space by going down. Let's start with pressure and Boyle's law. No, not this type of Boyle, this one. Boyle declared that pressure and volume have an inverse relationship, so as the pressure on a body of gas increases, the gas's volume decreases, and vice versa. When I take these balloons down to 46 feet, they will shrink and become less buoyant than they were on the surface. And when I bring this Diaflag's compressed styrofoam noodle back up to the surface, it will expand to its original volume. When standing at sea level with the weight of the atmosphere pushing down on us, we say that we have 1 atmosphere of pressure on us, which is equivalent to 101,325 pascals of pressure, or 14.7 pounds per square inch. When a diver descends, they experience additional atmospheres of pressure. An additional atmosphere in saltwater is about 33 feet, whereas in freshwater it's about 34 feet. The difference in depths is because saltwater is denser, meaning it has more mass per unit volume than freshwater, thanks to all the other substances suspended in it. To estimate a gas's volume, you can use this equation. This concept is the root of most dive maladies because, when underwater, a diver is breathing condensed air into their lungs. This would be like filling a balloon all the way under pressure. If this balloon were to ascend without letting any of its air out, it would burst. The same is true for the lungs, and overexpansion injuries comprise the bulk of dive maladies. On land, we call the force exerted on us by the ground the normal force, and it's always perpendicular to the surface. In the water, there's a similar upward force called the buoyant force, which in some situations can counteract or overcome gravity. Archimedes' principle provides an equation to calculate this buoyant force, and when compared to gravity, we can determine if an object will sink or float. Back to this styrofoam noodle. At the surface, the styrofoam has the same mass but more volume, and FB is greater than FG, so it floats. However, as the styrofoam gets compressed down at about 45 feet, it's denser, it has less volume and the same mass, and Fg ends up being greater than Fb, so it sinks. Divers use a BC, or buoyancy compensator device, which has an adjustable air bladder so that they can change their volume without really changing their mass. Together with lead masses, these allow divers to reach an equilibrium between the buoyant force and the force of gravity, giving the effect of weightlessness. This is why many astronauts are required to train in scuba diving before going into outer space. They can acclimate to the lack of gravity and learn how to move in a more controlled and better studied field. It also allows these space explorers to experience pressure changes and problem solve while relying on equipment to supply them with breathable air. However, astronauts can't just dive and then fly. The air we breathe is not all oxygen, and our bodies do not have use for the nitrogen we breathe in. When breathing compressed air underwater, our bodies can't off-gas the nitrogen as quickly as we are inhaling it, so it stores these tiny nitrogen bubbles in fat tissues, air cavities, and even the blood. This is no big issue if the body has time to properly purge this gas when at shallower depths, but if divers speed to the surface or fly and further decrease atmospheric pressure, these bubbles can expand and block blood flow, leading to serious health issues such as embolisms. Thanks for watching! Tune in next time to see how the density of water affects waves such as sound and light. Bye guys!